Well, let's start. Thank you, Matteo, for your introduction, and thank you very much for giving me the chance to be here and present my work. This is I'm very happy to see all of you, even though in the tiny box here in the video. I miss going to conferences and meet everyone in person so much. I guess everyone is missing this a lot. My work today, what I'm presenting, is a bit of a summary of what I've been doing in the past 2-3 years in the mostly numerical modeling of multi-phase flow and flow boiling in confined geometries. So I must have my list of contributors here that span from a supervisor like John, Omar, and Beatrice in Bologna, where everything started, but also include Federico and Andrea, who were postdocs who work with me now and in the past to develop all these methodologies. And just a quick outline. I think I have to start with just introducing who am I, because I guess that most of those in the audience never heard of me. So I think it's a duty to explain what my background and motivation of the study I'm going to present, numerical methods and challenges, and then I have in mind 3 studies to present. The first one on dynamics of bubbles in confined geometries in adiabatic flows, that opens the way to understand what is going on when we trigger boiling. If I have time, I would like to introduce a little study I did a few years ago, but that I think is relevant, which is on the undulations that appear on bubbles in small channels, and they may be influential in triggering dry out under certain conditions. So who am I? I like to start with the fact that I was born in a tiny village in the east coast of Italy, which is called Gradara, and it's relevant because it has a very old, one of the best preserved medieval castles. And Matteo has Monica Bellucci coming from his birthplace. He has his own reasons to be proud of it. I don't have such a beauty, but we have a nice castle, and all of those visiting around, I suggest to take a stop here. I was in Bologna for my PhD in energy engineering, working with Beatrice Pulvirenti. I did a postdoc in Lausanne with John Tome, another postdoc at Imperial College with Omar, and as Matteo introduced, I'm in Nottingham since 2 years. You can see that there is a linear trend, a linear trajectory that puts me directly in Iceland or Greenland in a few years. So you may need to come and visit me there. And this is just a bit of a summary of the research I've been doing in the past years, from flow boiling to evaporative cooling of fuel cells, bubbles through vertical root bundles, a bit of molecular dynamics with colleagues at Imperial and Brunel. Wax deposition in oil flow was my project when I was a postdoc at Imperial College. And I've also been working recently with Princeton University on bubble dynamics in vertical capillaries. But today I'm going to talk mostly about top left here, flow boiling in microchannels. So when I think of the motivation behind why I do this study and why I choose certain fluids, certain working conditions, certain geometries, well, all these studies were originally intended for thinking of two-phase flow as a mean to cooling down computer chips. So I took this data here from the literature that shows that we are currently getting into 100,000 watt of thermal design power of microprocessors. So this is the situation where we are now. So for example, if we want to convert these into heat fluxes, my collaborator Federico is now using a monstrous workstation with 32 cores that has a thermal design power of 280 watt. I found the die size in internet. I'm not sure how accurate is this value because it looks quite small. And the heat flux, if I didn't do some horrible mistake, it's on the order of megawatt per square meter, the heat flux we need to dissipate from such a CPU. If I take the CPU installed in Archer 2, that is UK's tier 1 high performance computer, we get same thermal design power, slightly larger die size, still heat fluxes on the order of the megawatt per square meter. Now, I did just a quick and dirty calculation. If we want to estimate the heat transfer coefficient we need to dissipate such heat fluxes, I take as wall temperature, I take the maximum temperature that we want to reach with our CPU, let's say below 65 degrees Celsius, possibly. Temperature of the fluid taken, for example, by cooling down the fluid at ambient temperature. We need heat transfer coefficients that are on the order of 10, 20 kilowatt per square meter Kelvin. So we know that the heat transfer coefficient is related to Nusselt number, thermal conductivity, and inversely proportional to the, let's say, a length scale of our problem. So here we see that reducing length scales, we should possibly get high heat transfer coefficient. That's where the idea of the multi-microchannel heat sink comes from. Of course, this way we also influence the numerator here, the heat flux, which should divide it by the total area, but let's take it just as a rough calculation. Now, if we consider, for example, microchannel liquid cooling, so single phase cooling, the flow is most likely to be laminar in these conditions. We have the good and old Shine London book that gives us Nusselt number for fully developed laminar flow in non-circular channels. Case 1, the blue line, is the situation in which the heat is uniformly distributed. We see that we range between 4 and 8 of Nusselt. But case 2 and 4 are more realistic of what happens in a microevaporator where the heat is not uniformly distributed, and we are still capped by maximum Nusselt number of 8, which becomes even smaller if we consider heat coming only from one side. So this is just to say that Nusselt number for single phase flow we know is limited to the value of 8, and of course if we can increase the Nusselt number we get a larger heat transfer coefficient, which is ideal. What's the potential that two-phase cooling can bring to such heat transfer problem? First of all, when we move to microchannels, flow patterns that they mostly appear are slug and annular flow. So in the slug flow, we have long bubbles with very thin films around. And in the annular flow case, we have continuous gas core at the center and a thin film around the channel perimeter. So slug and annular flow, the heat transfer is very much related to the thickness of this liquid film. If we do another rough estimation, here I'm just drawing a sketch of a rectangular channel cross-section with a film of liquid covering the wall. If we solve a quick one-dimensional steady-state heat conduction problem through the film, which is quite reliable when the film is not, let's say, moving too fast, so it's quite reliable if we are talking about slug flow at least, we see that the heat transfer coefficient is directly calculated as thermal conductivity of the liquid divided by the thickness of this liquid film. And if we back calculate then the Nusselt number, we see that an estimation of the Nusselt number we can get with a thin film covering the wall and an interface at the saturation temperature can be estimated as the ratio of hydraulic diameter divided by liquid film thickness. So this is an important outcome, and it tells us that potentially we can get very high Nusselt numbers with this methodology. Of course, the evolution of this liquid film is crucial here. Not too thick, not too thin, because otherwise it would dry due to evaporation. So this is where I've done a little bit of work that I'm going to present today. This is just an introduction about some experiments we did when I was at the PFL. I was supervising a PhD student, 𝗟𝗶𝗾𝗂𝗏. She was doing experiment to characterize micro-pin-fin evaporators. So small evaporators with series of micro pillars to be used to cool down CPUs. And she was applying high-speed flow visualization from the top, infrared thermography from the bottom of the test section, to extract resolved field for temperature, and we were having also high-speed images from the top, but we didn't do much with those. But with this experiment, we were extracting, for example, heat transfer coefficient at the wall as a function of the, let's say, streamwise direction. And the resolution that we could get with the infrared was in the order of 80 micrometer, with a high-speed camera was in the order of 10 micrometer. These are the frequencies we could get with infrared camera and high-speed camera. Still, even though these were quite advanced techniques, if we really want to characterize what happens at the bubble level in a microchannel, we need spatial resolutions that are below the micrometer and frequencies that are way above 1,000 Hz, which makes it quite difficult for experiment to really get into complete spatio-temporally resolved data. That's where simulations can be helpful to try to get into the details of the flow. Of course, these simulations are not free of difficulties. Especially each flow pattern has its own challenges for an accurate numerical modeling. If we take a look at the bubbly flow region here, the bubbly flow region is very much dependent on the frequency of bubble generation. And to really get a good insight into what happens at the level of bubble generation, because bubble generation, it comes from molecular dynamics. So the continuum simulations I'm talking about are not enough to really get a grasp of what is happening there. Here I'm just showing an image of a work on which I participated. I didn't do much in the work. I mostly collaborated with Alessio, Omar at Imperial College, and Edward Smith at Brunel University, and they are working on numerical simulations of bubble nucleation to study the effect of the cavity geometries and cavity size on bubbles using molecular dynamics. What I've been really involved into is on the analysis of the slug flow regime that comes after the bubbly flow regime. The difficulty of slug flow is to really catch and fully resolve the thin films around the bubble where most of the heat, mass, and momentum transfer happen. So in the next slide, I'm going to start presenting two works that I've done on this aspect. I will start with presenting a work on adiabatic flows, so no heat transfer, no phase change, just to get the basics. And then I will move to what happens when we have boiling flows. I hope that everything is fine. I hear some noises on the background, but I hope you're still hearing me and everything is well. Okay, so who cares about film distribution in confined flows? Of course, we look at it from the point of view of microchannel evaporators, but the model of bubbles moving in small gaps is relevant also for colloid detachment and transport, for example, in unsaturated porous media, to study the motion of pollutants, bacteria in unsaturated soil. Also, these kind of bubbles in small channels have been used as a method to clean up medical surfaces which were polluted with adhered bacteria. And bubbles or droplets in microgeometries are also a model for the delivery of drugs in lungs and for medical treatment of diseased lungs also. And as well, bubbles are also a model for, not a model, but really what is happening in, for example, this case of membraneless electrolyzers for hydrogen production, where the dynamic of these bubbles is very important. What do we know about bubbles in confined channels in adiabatic flows? For circular channels, we know quite a lot. We start from Bretherton theory, which is 60 years old. Bretherton studied theoretically the motion of very long bubbles in capillary channels in the limit of small capillary and Reynolds numbers. He has a lubrication theory that is able to predict the film thickness of these bubbles. In the case of circular channels, bubbles are usually long. They have an annular liquid film which is constant in thickness. And the Bretherton theory gives us a way to calculate the film thickness as a function of the capillary number only. Capillary number is the ratio of viscosity and surface tension effect. Now, this is valid at very small capillary numbers, and it has been extended by 𝗟𝗆𝗆 and 𝗟𝗆 about 20 years ago to cover larger capillary numbers. More recently, it has been extended by 𝗏𝗏 to cover also the effect of inertia on the flow, so Reynolds number which are up to the turbulent flow regime. So these correlations are quite trustable, and they can give us full idea of the film thickness depending on capillary and Reynolds number. A work that I did a few years ago that I will present at the end of my presentation today, if there is enough time left, is on extension of Bretherton theory to actually introduce inertia into the flow equations and retrieve, by the solution of the ordinary differential equation, retrieve the full profile of the bubble from the nose to the tail, also including these undulations that you see on the surface of the bubble that appear when the Reynolds number is much above 1. We know a bit less for what concerns non-circular channels. We have one theory from 1995. One resolved the partial differential equation governing the film, in this case here in 2 dimensions, using asymptotic theory, and he gave us some scaling analysis that tell us that the film thickness along the channel center would scale with capillary power 2/3, but because of the corners of the channel, there is this interesting profile of the bubble for which there are some minimum film thickness region where the film thickness actually scales with capillary number power 1. And these are of course important because if there is a risk of dry out, this is where it's going to start. Now, there are also some more recent numerical simulations done by Delozar and some others who actually look at extending the study for larger capillary numbers, and they also did a systematic study for different aspect ratios of the channel. This is a plot that shows finger width, which means the width of the bubble in the cross-section as a function of the capillary number for different aspect ratios. Still, they provide information about some sort of integral quantities, but there is still a bit of open space here to play about what the cross-stream film topology, for example, what's the minimum film thickness here as a function of capillary Reynolds number? What's the stream-wise film topology? So how does the film evolve in the flow direction? What happens when the Reynolds number is above 1? So this first study that I'm going to show tries to respond to these questions, and I'm not going into the detail of the numerical method. I'm using OpenFOAM, which has a solver based on the volume of fluid method. The first study on square channels will use a traditional VOF method. The second study on rectangular channels will use a more advanced method to calculate the interface curvature that is crucial in the surface tension force estimation. Range of non-dimensional parameters I'm studying, we go from very small Weber numbers, which means viscocapillary flows, up to Weber numbers of order 100, which means strong inertial effect, aspect ratios from 1 to 8. So we start with the adiabatic flows, like I said, and this is an important figure to look at. We are considering our bubble translating now in steady flow conditions, and we take a cross-section in the bubble flow, and we take a look at the cross-section of the bubble. You see in blue the region occupied by gas, in gray the region occupied by the liquid. We can identify a radius of the bubble along the center, a radius of the bubble along the diagonal. When we plot these two radii as a function of the capillary number, in blue we get the one at the center, in red we get the one along the diagonal. We identify a few regimes. Larger capillary numbers, so it means bubble is moving faster. The bubble is essentially a cylinder, even if the channel has a square cross-section. So center line and diagonal radii, they match. You see they have essentially the same values, and reducing the capillary number, so reducing the bubble speed, the radius of the bubble increases, so the film thickness reduces, which is quite standard, quite traditional. But then we start getting into interesting dynamics when we reduce the capillary number and we start getting into the region in which the center radius cannot increase anymore because of the presence of the wall. The radius along the diagonal can still increase, so the two radii, they start to diverge. If we further decrease the capillary number, which means we slow down the bubble, we see that there is an inversion in the curvature of the bubble profile. Especially, we get an inverted curvature along the channel center, which triggers a minimum film thickness region here, as predicted by Wang theory and as shown by many others before. Now, in heat transfer, we are interested in film thicknesses because that's tightly correlated to the heat transfer coefficient. So let's now take a look at the film thicknesses. Let's start with film thickness along the diagonal here. So this is the same figure that I showed you before, but instead of looking at the bubble radius, we look at the film thickness. So I put also as a reference the film thickness in the case of a circular channel, which is given by the correlation of � and 𝗟𝗆 that I presented before. And we see that the film thickness along the diagonal is much larger than what we get for a circular channel at the same capillary number. However, if we look at the film thickness at the center, as we can imagine, this gets very small as we reduce the capillary number. And importantly, this is much smaller than what we get for a circular channel. And if we take a look at the minimum film thickness that we get at the dimple here, this is increasingly smaller as we reduce the capillary number. And it achieves an asymptotic scaling here, which is proportional to capillary number power 1, which agrees quite well with Wang's theory. This is an important outcome because in many cases, when we study flow boiling in a circular channel, we sort of try to extrapolate correlations for the film thickness in circular channels to square channels. But as you can see here, film thicknesses may be 1 order of magnitude smaller in square channels. So this is very important to account for when we want to rationalize flow boiling results. There is another interesting aspect that concerns the streamwise film topology. Here I'm looking at the bubble from the top. Bubble is moving from left to right, and the colors that you see represent the film thickness. And so the red regions are the thinnest films. Here we get the bubble nose. You see that there are these 2 streaks of thinnest film that develop. So if I extract the film thickness along the thinnest region here, along the white dashed line, I see that the film keeps decreasing even when the bubble is quite long. We tested this also for bubbles that are like 20 hydraulic diameters long, and we see this continues happening. If we take a look at the same graph, exactly the same graph, but in a log-log coordinate, we see that in log-log coordinates, the film profile is sort of linear. And this is an interesting aspect that is repeated also when we change the capillary number, even though the slope slightly changes. And if we put together the slopes of those slopes, or at least those coefficients for the power law, for the different capillary number, we see that decreasing the capillary number, we get an exponent that seems to get to 0.5, which matches very well a theoretical paper presented by Kreutzer a few years ago for the drainage of liquid films in the presence of channel corners, with the difference that they were considering the drainage in time. But in our case of steady moving bubble, time is directly related to the distance from the bubble nose. So the exponent that we get makes sense with the theory that they present. Now, let's move to the rectangular channels, which is an ongoing work and is still unpublished. What I'm looking at here is exactly the same I was looking at before in square channels. I'm considering a cross-section along the bubble body. I'm taking a look at the liquid film distribution, and what I'm extracting here is the bubble width along the longer side of the channel as a function of the capillary number of the bubble. The solid lines that you see are the simulations of 𝗟𝗏𝗁 et al. That I introduced a few slides ago. So we use their simulation data as validation data for our simulation. I do this because their simulation were validated with some in-house experiments. So I trust their numerical method very much, also because it's a finite element method, boundary fitted method, very accurate. So I think it's quite trustable as a benchmark. And we get very close to what they present in terms of results. And if we take a look at the cross sections, aspect ratio 2, aspect ratio 4, aspect ratio 8, qualitatively, we see that the flatter the channel, the thicker the film at the sides becomes. Now, I want to take a look at the liquid film thicknesses. So now I focus on the liquid film thickness on the side, and nothing very surprisingly happens compared to what we saw in the previous slide. Increasing the aspect ratio of the channel, so making the channel flatter, gives larger field thicknesses, even though there is a change in trend at the smaller capillary numbers, because at smaller capillary numbers, we would have also a dimple on the shorter side. When we take a look at the film thickness along the shorter region, we see an interesting aspect, which is that as we increase the aspect ratio and as we increase the capillary numbers, we see that all the film thicknesses, they seem to collapse along the same curve when we rescale the film thicknesses by the channel hydraulic radius, right? Now, we actually put together some different theories into one that is able to actually explain this trend that we see. If we put together Wong and 𝗟𝗏𝗃 theory, we get a correlation that tells us what this film thickness should be when we rescale it by the radius of curvature of the meniscus at the corners, which should be a function of the capillary number only, even though we expect the radius of curvature of the meniscus to be a function of hydraulic radius, aspect ratio, and capillary number. However, from Wong theory, it turns out that if the capillary number is not massively high, the radius of curvature of the meniscus is actually quite constant as a function of the hydraulic radius of the channel and does not depend on the aspect ratio nor on the capillary number. So if we put this red box into the correlation I put up here, we get a correlation which looks exactly the same as the one for circular channels, but divided by a factor 2. And this explains very well the results that we see here. So this is, let's say, this concludes the part about isothermal flows. Let's now try to use this reasoning to rationalize some heat transfer boiling results that we obtained. What we have done 1 year ago, we studied the effect of the aspect ratio on channels when flow boiling happens. We did this because in the literature, we see that there are many different aspect ratios in experiments that are studied for multi-microchannel evaporators, and there is a bit of disagreement on which aspect ratio maximizes heat transfer. So we wanted to try to use numerical simulation to get a look into this. So the method is, again, open form extended with a phase change model that we took from the literature and we implemented. So here you see a video of a typical test case, which is the evaporation of a bubble in an infinite liquid. We used a phase change model that comes from Schrage and Tanazawa theory. So there is a background theory on the evaporation model that we are using. It's a model which is quite standard for continuum simulations of boiling, so there is nothing really special in it, but I can provide background if anyone is interested. Now, we further validated our model for boiling flows. We took an experiment from Mukherjee in 2011 where they did some experiment in boiling of water. And even though they didn't measure heat transfer, they provide the bubble volume as a function of time. So we tried to reproduce their experimental conditions by inputting a tiny bubble at the center of the microchannel and tracking the bubble versus time and measuring the equivalent diameter, and we get a very good agreement with their experiments. So we are quite confident that the numerical model should be reliable. Now, the numerical setup for these simulations, let's call it idealized. We have a uniform heat flux around the wall in the heated section of the channel. Why uniform and not like one-sided or three-sided like in typical microchannels cases? We have done this just to make it more simple, to keep a uniform heat flux so that we can understand what is going on without adding the complexity of a non-uniform heat flux, which is something that we're studying now. So aspect ratio 1/8, a range of capillary and Reynolds number which is applicable to refrigerants at typical conditions of two-phase cooling of electronic chips. Prandtl number taken from a typical fluid at typical conditions. Low heat flux, as you see here, we are at the order of 10 kilowatt per square meter. Again, to keep a bit the model simple. We are now working on larger heat fluxes, but what I'm presenting here is at lower values, 10 kilowatt per square meter. So what we get from a simulation of this kind, the bubble starts in the adiabatic section. It starts growing in the diabatic section where there is the uniform heat flux. The nose accelerates, and here we see on the right the bubble colored by the evaporation rate. So we get an idea about which regions around the interface that contribute the most to the liquid to vapor mass transfer. These regions are close to the nose. As you can see, those are the regions that get the whitest. So first of all, let's take a look at the bubble dynamics that we get from these simulations. I'm looking at the channel from the top. I'm looking at the interface profiles, aspect ratio 1 square channel to aspect ratio 8, a flatter channel. We are keeping the hydraulic diameter constant for all the different aspect ratios, constant inlet speed, which means constant mass flux, constant initial bubble volume, and constant heat flux four-sided. So what we see immediately here is that increasing the aspect ratio, the bubble grows more slowly, which is due to the fact that the bubble needs to first become as big as the channel and then elongate before growing in the streamwise direction. When we take a look at the bubble speed versus streamwise location of the nose, we see that increasing the aspect ratio, as we could imagine from the figure on the left, the bubble speed decreases, and we proposed a simple method to estimate the bubble speed, and we see that the bubble speed, it actually scales as aspect ratio divided by 1 plus aspect ratio power 2. So the bubble speed should decrease, increasing the aspect ratio. Taking a look at the heat transfer now, we are looking at the temperature field in the cross section. So this is the square channel. We see that the corners are the region where that stays at the larger temperature, because the interface is effective in reducing the temperature of the liquid down to the saturation temperature, but the corners are too far from the interface, so they don't really feel the effect too much. And when we look at aspect ratio 2 and 4, there is nothing more to say compared to what we have already seen from the square channels. The corners are always the hottest regions, and some of you may think, well, these corners, they may actually trigger new nucleate boiling, and this is very much true. We don't have it in the simulation for now. So in the simulation, we start already with a bubble, but the corners are points where actually there can be nucleation, and that's something that we are investigating now. When we look now at we try to link film thickness and Nusselt number. I'm looking at the square channel here, and I'm looking at the bubble from the top. So the bubble is moving from left to right. The white line here shows the bubble interface, and the colors, they represent the film thickness. So in red, we see again the regions where the film is the thinnest. And as we expect, we see on the right the Nusselt number, and we see that there is a perfect correlation of the highest Nusselt number that are detected where we get the thinnest films. So nothing surprising then when we move to aspect ratio 2, we see that the largest Nusselt number are detected where we get the thinnest films, but the two streaks where we get the largest Nusselt number, they get farther from the channel center, and this is normal for increasing aspect ratios. So this is also what we get when we have aspect ratio 4. There is nothing. We see that the dynamics become quite, it's in line with what we would expect. So what we have done after this is to put together all the simulations we have done. So for every aspect ratio, we fix here the flow rate, we fix the capillary number, and I'm measuring an average Nusselt number by taking the average of the Nusselt number in all the walls. Now, the black diamond here, the total, is the average in all the perimeter. The blue is the average only on the top surface, which means the longest side. The red is the average on the shortest side. It's top and side, but because it's uniformly heated, let's just say that the top is the longest wall, the side is the shortest wall. So along the side, when we increase the aspect ratio, we start getting these thicker films. That's the reason why increasing the aspect ratio along the side, the Nusselt number drops. So at small capillary numbers, small flow rate, we see that total heat transfer coefficient, let's say total Nusselt number, the square channel gives the largest heat transfer coefficient. And this happens because the square channels get very small film thicknesses at low speed. But at the same time, we should consider that this film may actually evaporate in situations where the heat flux is much larger than what I'm testing here. If we increase the flow rate by a factor 10, then if you remember, the square channel gives a cylindrical bubble with very thick films. And so what happens is that actually we get an inverse trend where the square channel gets the lowest heat transfer coefficient, whereas higher aspect ratio channels, they promote the formation of a wide, thin film that gives, that increases the Nusselt number sort of asymptotically as we increase the aspect ratio of the channel. Let's skip this figure, which is just extra data on what I showed you before. I just want to get now quickly into a project that we just started, funded by EPSRC, with Imperial College, with Christos Markides and Omar Matar at Imperial College and Tassos Karayannis at Brunel University. We are trying to get simulations and experiments of flow boiling in small channels to get together. So we just started the project, but what we are trying to do in Nottingham is to reproduce at the moment experiments done at Brunel University. They have experiments with multi-microchannel evaporators, and we are trying to reproduce their experiments. So what you see here is a square channel, one of their experimental setup. This time with a wall with a heat flux coming from the three walls, so bottom wall and the side walls. We initialize a tiny bubble up here at the corner, and we see the temperature field here. on the figure here at the center in blue, we will see the dry patches.
No.
On the box on the right, we will see the
No. What's the last name?
Is someone asking anything? Matteo, is everything all right?
Yeah, I think you can continue. Someone unmuted himself, but it's fine.
Okay. Just to conclude here, so this is a simulation where we want to take a look at what is going on in the channel and possibly extract heat transfer coefficient. So we see here the evolution of the dry patch, and here we are taking a look at the energy source at the wall. And what we are trying to do now, we are still at the development of the numerical model, because we are trying to add adaptive mesh refinement to our numerical method, and adaptive mesh refinement will be crucial here to be able to capture the thin films with adequate resolution. I have a last study here, but I'm going to skip this for the sake of time and to give space to questions. We studied the undulations on the surface of long bubbles appearing in high Reynolds numbers. This is just to say that we extended lubrication theory to include Reynolds number effects, and we were able to predict the undulations on the surface of the bubbles. I just keep all this part and I move to the end. We were able to predict the undulations and to characterize film thickness in the presence of the undulations in the adiabatic case, which is of interest because if dry out occurs in circular channels, most likely it will happen on the top of these undulations where there is a minimum value of the film thickness. In conclusion, these are just open issues. What we miss from the numerical standpoint, we need more experimental data for bubble nucleation. We need more experimental data to understand what's the frequency of bubbles, how it depends on flow parameters in microchannels, possibly coupling with molecular dynamics and mesoscale method. There is a very good, interesting paper that has been published by Francesco Magaletti at Brighton University on using a phase field method with the fluctuating hydrodynamics to study nucleation. That's a very interesting approach. We should find a way to implement surface roughness information from experiments, because when we study fluid microchannels, the surface roughness becomes very important. Roughnesses in microchannels, they are on the order of hundreds of nanometers. So it becomes difficult to implement micro-layer models that start from an absorbed evaporating region, which is of nanometer length. We need more data about temperature field from experiments, which are crucial for our initial conditions, in order to approach initial and boundary conditions in the experiments. I leave this slide here. I'm curating a training for OpenFOAM that I put in the Virtual Institute website. It's accessible to everyone. If you have master students or PhD students who would like to start playing with OpenFOAM, I suggest you to take a look at that. I develop a virtual machine and some test cases that are useful to start playing with that. This is all. I hope you could enjoy a little bit this talk. Thank you for your attention.